Hi, folks. I got a quick discussion about generators and on a tangent on motors. And if you need a moment to pause the video and copy down all the stuff here, please go ahead and do that now. All right. Now, you might recognize this. This is from early in the unit. We had a rotating circle conductor in a magnetic field. And I gave you information. I said it was rotating at a frequency F. In a magnetic field strength B, and the area of the loop was A. And we calculated the voltage generated by that rotating loop in the magnetic field, and I've written that answer down here. And as a reminder, it would look like this. So you'd have a magnetic field created by that magnet, which would point up. And if you rotate the loop in the magnetic field, you get a sinusoidal voltage, okay? Now, the only thing that I might do to modify this equation is if I had more than one loop. So let's say I stacked, n number of loops on top of each other, then all you would do is multiply this whole equation by n, the number of loops, okay? Now, why am I bringing this up now? Well, let's talk about the power company for a minute. Now, here in Illinois, our power company is ComEd or Commonwealth Edison. So this is how they generate all of their, or virtually all of their electric energy, is somewhere there's a generating plant or plants, and there are coils of wire being turned next to a magnetic field. Now, it wouldn't look exactly like this, but it's the same idea, okay? Now, what changes over time? So over a course of a day or a week or a month, what about ComEd changes and what cannot change, okay? Well, if you're at ComEd, you cannot change the frequency. That is 60 hertz in the United States. And our electronic devices are designed to work off of 60 hertz. You cannot change that. They are not going to change B or A, or for that matter, N. So in other words, they're never going to change the voltage. Our electronic devices rely on a specific voltage. For us, United States, it's 120 volts roughly. At 60 hertz. So if ComEd were to change voltage, that would be very bad for a lot of our electronic devices. So what does change over the course of time? Well, for any generator that works like this, something has to rotate that coil or coils, okay? And that is something mechanical. Something is rotating that coil, okay? And that rotational energy is then turning into electric energy. Now, we're going to look at the rate at which that's being done, and that's power. So there's a couple equations for power that we know. We know for electrical power, one equation is I times V. Now remember, E is V, okay? This is just, EMF is just a voltage generated in this manner, okay? I is the current, P is the power in watts. So that's the output. That's the electrical energy we're getting out of this thing. What kind of energy are we putting into it? Well, we're rotating it. So rotational power is instantaneous, is torque times omega. Now, technically, it's a dot product, but here we don't have to worry about that, okay? So if you have a generator that's 100% efficient, torque times omega is I times V. Now, of course, nothing is 100% efficient, but for the sake of argument, we're going to pretend it is right now. And what we're going to do is we're going to rearrange. We're going to solve for torque. Torque is V over omega times I. Okay, so what changes over the course of a day or a week or a month? Current. All right, so you cannot change the voltage, and our house has got to be 120, so ComEd's got to generate a voltage specific to the plant. And omega has to be 2 pi f, and f is 60, so omega has to be 120 pi. You cannot change those two numbers. They have to be a constant. But what does change is current. So let's say in the summer, we all switch on our air conditioning, okay? Well, if we all switch on our air conditioning, that demands much more current. Therefore, ComEd's generator takes more torque to turn it. So the current, that's called the demand, and how we meet the demand is how hard we have to push or pull to turn that generator, okay? So now any power plant has a maximum torque that they can develop. Just by the physical nature of the plant. So if you try to draw too much current, if the population tries to draw too much current, the power plant could fail, or you might get a brownout or a blackout where they have to shut off parts or all of the current to keep the plant running. Okay. Now, some other things about generator. So what makes this thing spin? Something has to spin it. Okay. Well, in the old days, it was like a coal-fired power plant. You would burn coal. It would heat up a vat of water, enclosed usually, and that water, when it heated up, became a high-pressure steam. And then you would let that high-pressure steam go through a turbine, which is basically a fancy fan. And that fan would then be attached to this coil of wire right here and make it rotate. So you turned chemical potential energy of the coal into thermal energy, heat, which then turned into mechanical energy of the rotating coils, which then turned into electrical energy. So by the way, not the most efficient way to generate anything. When you're transforming 4 different types of energy, you're going to lose some in each of the transformations. Okay. Now, nuclear power is, while it may sound really different, is actually almost identical. The only difference is what heats up the water. So in a nuclear power plant, you have nuclear fission, which is the breaking down of large elements into smaller ones. When you do that, you lose a little bit of mass, which turns into energy, heat. And that heat heats up the water, which then boils and turns into high-pressure steam that goes to your turbine again. So the back half of a coal-fired power plant and a nuclear power plant look identical. Okay. For a wind turbine, you don't have to heat up anything. You just run the wind directly through the turbine, which then turns this coil of wire. And like a hydroelectric dam, the water directly turns the turbine, which turns that coil of wire. Now, there are different kinds of energy sources, which we're not going to talk about too much. But so, for instance, photoelectric solar energy, that's a totally different ballgame. They're not turning anything. They're turning thermal energy directly into electrical energy using a photovoltaic cell, and actually light energy directly into electric energy using a cell. That's a different story. But anything that involves motion like this is how it works. Okay. Now, a motor, this is a generator. So a generator takes mechanical energy, power, and converts it to electrical power. So in this case, somebody is turning that coil of wire, that's mechanical energy, and turning it into electrical energy. Electric motor is basically the same device. Okay, let me see if I can scroll that. Oh, maybe it was up here. Let's see. There we go. And for the motor, you have electrical energy input, in this case a battery, and that creates a mechanical energy. So a motor and a generator are basically the exact same device, okay? Just rotating a coil of wire and a magnet. If you are rotating the coil of wire, you're treating it as a generator. If the electrical energy is rotating the wire and making mechanical energy, well, now it's a motor. So for instance, if you took a house fan, unplugged it, and plug the voltmeter into the 2 prongs of the power cord, and you turn the fan yourself, you would see voltage generated at the prongs of the plug. So motors and generators are the same device, just they're used differently. Okay. So I do hope that you have a little better understanding of electrical power generation and what goes on. And thank you very much.